So I promised a final analysis on why I decided to replace the output transistors in my Ampeg SVT-3 Pro in a different video. Cards somewhere, links somewhere, I don't know, whatever. Um, Basically, what we're looking at here in the charts is a rundown. I removed the devices and I used a peak device tester. It's the DCA Pro 85, 75. Again, link will come at some point. Uh, Helpful largely because it would trace a curve. I don't have a curve tracing device that will generate a screenshot or comparison devices, and the software that comes with this is actually really good. It'll do comparison traces of what would appear to be an infinite number of devices, although eventually the color reuse gets to be a bit of a problem. So, following the scratchy output, cutting out, so on and so forth, failure to bias, I had noticed eventually that we basically got into a situation where the amplifier could not be reasonably biased well enough to, within the specification of the manufacturer, to reliably operate. And that was made worse with temperature changes. Once we would get into fall and winter and it gets cold down here, the scratchiness would come back with a vengeance. Believe because either the output devices or the potentiometer used for the trimming, which I should eventually replace at some point, but I just don't feel like dealing with it right at the moment, are not up to snuff. In the case of the output devices, it's largely because of the age. Sorry about that. It's largely because of the age of the devices and the fact that they've been run out of spec for so long. In the case of the pot, I've read on TalkBase that it has a lot to do with the fact that the part originally specified was not very good. So, that all in mind, I pulled the parts. I had an order coming with 8 each IRFP 240 and IRFP 9240. I don't remember. I think it's the first one is the N channel and the second one's the P channel, but whatever. They're on Mouser. They're fine. They're parts. They're Lego. So I had 8 of each coming. I figured with a total of 12 of each device, I should be able to find a set of 4 of each that would be within reasonable characteristics of one another. Before any of those spare parts came, I ran some graphs. You see right here, this is the ID VGS, so current drain, measured with varying the voltage from gate source. This is for the original 9240, or no, I'm sorry, the original 240s. As you'll see the file names scroll by up here at the top. So I wasn't sure what to expect originally because I measured these and I said, well, they're not the same. Is this bad? I have not seen a curve of any of these devices, and it roughly measured or matched my expectations of what the curve should look like. Then the new devices came, and when you plot the two of these together on the same chart, you can see all 8 of the new devices come in at the same curve shape, same voltage levels for current, pretty closely tracking with one another. So, looking back at the notes from before, unfortunately, the hot transistors were numbers 3 and 2, and the cold transistors were number 1 and 4. So if we go back to here, numbers 1 and 4 are the red and light green, so those are the cold ones. Those are the ones that were showing the nearly off voltage measurement across their bias resistors. The other two, you'll note, are way closer to what came out to these. So you have the original cold resistors, one of the hot resistors, or transistors, another one of the hot transistors, and then the new grouping. So I knew just from this that I was going to need to take a slightly different approach to doing this, that there's going to be a bit of trial and error involved. So I had to reconcile with myself that it was okay to do this, because if I messed it up too bad, I'm looking at I forget how much it costs, probably about $300 power board replacement, which is fine. If the power board's not working, if it's broken, you're not going to break it any further, right? So I called it a night at that point, I think. Yeah. So I finished measuring. So these are the drain current with the varying the voltage from drain to source. So you can see again here we have two, 1 and 4. The cool ones are off in the weeds, and 2 and 3 are the hot ones. They were pretty tracking closely with one another. By that standard, it sure seems like the 2 cold ones were actually the problem, but whatever. Anyway, the point is, here are the new ones. So you can see there's quite a bit more variability. The vertical scale is a little bit shorter on this because they're all closer to one another, but you can see they vary pretty substantially from 2 3/4 to 3.5 milliamps once they're on. Here they vary from about 2.5 all the way up to just over 4. So you can see there's quite a bit of change there. Anyway, so they're all the new ones basically were right in the middle of all the old ones, with the exception of number 4 of the originals. I don't know why I included this, but basically you can see that there are the clusters in the middle, and then the new ones are clustered in the middle, and then the old 2 outliers are off to the side. I don't think this matching characteristic is as important as the voltage from gate source, but I included it anyway. Okay, so we move on to the 9240s. This is what I did the next night. So here's the current from the drain current, measuring current voltage drain to source. You can see we had 1 outlier. The other 3 tracked each other. There's interesting variability in shape to these traces relative to this, where you see that they're all straight lines once they get to the on point. These all have a slope to them. Now, I don't know, that may be a characteristic of the IRFP 9240 MOSFET. It is, apparently, but what's really interesting is when you take these new ones, you compare them to the old ones, and the shape of the chart, or the shape of the curves, isn't even the same. All of the old ones had significantly flatter curves than the new ones. Now, again, I don't know, maybe that's a characteristic of maybe that's a characteristic of the IRFP 9240. Maybe that's just a characteristic of whatever kind of MOSFET this is. But anyway, it just shows really how far out of spec the old parts had likely become. So here's the 9240 drain current plotted against a variable gate source voltage. Same as before, oddly, numbers 1 and 4 were the cold ones, and numbers 2 and 3 were the hot ones. And yeah, here's the new ones. You can see again, all pretty clear, and you can see that they're all trending toward that red line. They're all trending toward number 1 of this. So let me see again if the hottest original 9240. Okay, so these were the hot ones on the 9240s. These were the cold ones. So this curve trends the other direction from the 240s, and I think that's just a byproduct of them being N-channel versus P-channel. So again, we have all of the new ones that roughly track the coldest 9240, with the second coldest 9240 being relatively close, and then the 2 hot ones being way off on the left. And they were pretty close to one another, so perhaps there's a way to match those together. I don't know. Here are the tails, for whatever that's worth. Okay, so after some consideration, I decided to use 240s. Did I document that? Now they're written down somewhere. Doesn't matter particular. Run numbers 1, 2, 7, and 8 because they have the closest drain current plots. All the VGS drain current versus the VDS. The VGS were all way too close. The VDS, there was some variability, so I just picked the 4 that were the closest. For the 9240s, I went with 1, 2, 3, and 6 out of the new ones. So again, if we come back over here, 1, 2, 3, and 6 are all going to be in this cluster someplace. I may have looked at actual data points to make that decision night of, but those are the ones that I went with. So when I plotted the group together, this is what I ended up with. So these are the original 240s and 9240s. They're all over the place. And these are the new 240s versus the 9240s. The 240s are universally to the left of where the 9240s sit. I don't believe I mapped the ID VDS curve for this comparison, which would have been interesting to see, but I suspect you'd see that, you'd have the 9240s all close together, sloping off to wherever, and the 240s just sort of doing their thing. So, all told, put everything back together, got it all put in and hooked back up, and the fresh power on. Unfortunately, I made the original measurement with the load connected because I was interested in watching the oscilloscope trace. The oscilloscope trace, interestingly enough, and I'll see if I can dig up this this information real quick, but the oscilloscope trace for the original transistors basically was a noisy mess when you turn the bias all the way down. If you turn the bias all the way down, you would get a noisy triangle wave, triangle form. And if you do that with the new stuff in there, there's a little bit of noise, but it's flat. No, there's no crossover distortion just from idle line noise. It's so much quieter. So I'm just going to read some. Let me see if I can put. I'm just going to put this here. So this is what I wrote up on a YouTube comment, but the part that we're really interested in is great. Is this deal right here? So powered up, brand new. The new devices. Once I had the idle bias set correctly, were at 5, and you can see that the averages are within 4% basically of where the average is on both sides. The idle wall draw 0.79 amps at 117 volts. The original devices were all over the place. The averages were fine. 9.39 and 9.86 is fine, but this is why you don't just measure the average in doing bias calculations, because let's say that the average was at one point, I had a previous where the average was coming in at like 5, and I had one device that was over spec. It was at 28 millivolts. Once they started running the bias a little bit hotter and it started working the transistors a little bit differently, I guess that changed it somewhat so that the ratios came in closer. But yeah, you have to look at all of them. And if you can find and identify the hot ones, and there is just one hot one, maybe you can get away with just replacing that. But if you're going to do this with any regularity at all, or if you plan on keeping the amplifier alive forever, you're going to want a curve tracer. you can make the measurements yourself using a DC voltage supply and some resistors for taking the output load. But it's just so much easier if you have a device to do it for you and to make the charts. I mean, I didn't have to do any of this stuff by hand. So much easier to just have the device do it for you. So anyway, that is what we happen, where we are, why we are where we are. I'm still disappointed in the original, the folks that did the original testing that I asked for, probably about 10 years ago at this point. I paid them $100 to reflow some solder under some input jacks, and it didn't fix the amplifier. So it was a bit of a bummer, but it took me on a learning journey. And fortunately, SVT-3 Pros are cheap enough that I felt like I could make this happen. That it wasn't going to be a huge, terrible loss. You just have to be careful digging around in there, not short stuff out against one another. And you have to be willing to put the time in and track it over a period of time. That is if you're servicing your own stuff. If you're servicing somebody else's stuff, well, you don't have time to do that. So I guess on the one hand, I get it. The folks at the repair shop just weren't going to have the time to set this there and watch it for long periods of time and trace the bias. But yeah, that's where it is. So anyway, that is a potential resolution of problems. If you have one of these amplifiers, just see if you want to work on it yourself. Check the bias voltages and make the adjustments yourself. Just be aware that the bias adjustment potentiometer is phenomenally sensitive. If you want to have somebody else do it, have them check this. If the bias voltages are all over the place like they were in mine, you're probably going to need to replace the output transistors. The parts are not expensive. I think all told, including the attempt to build my own test rig, I spent about $45 shipped from Mouser, so a quarter of that was the shipping fee. Solder, if you've got soldering stuff, you're good to go. You can do this. You just have to take good notes about disassembling the device and putting it back together. So yeah, that's it. Feel free to drop comments or questions in the thing, and I'll see if I can actually bother to remember to check them.